Okay, so we learned that mathematicians don't like gray area. So they want a single number that will tell us whether a relationship is strong or moderate or weak. And that's called the correlation coefficient. We saw all these properties that it has. And so here I have, and actually, let me pick a different one there. So you can see perfect would be positive, perfect positive, strong positive, there's the 0.8, moderate, actually that's weak right there. And then this is terrible, 0, and so on. And then negatives are over here. Now the one thing to notice about the -1, just because it's -1 doesn't mean the slope is -1, right? It could be steep, it could be shallow. These are steep over here. This is shallow over here. +1, it could be very steep. That's like that. Or shallow, right? So 1 doesn't tell you your slope. 1 tells you the sign of your slope. So if you have perfect 1 or anything above 1, then a slope would be positive. Anything below 1, the slope would be negative. That's over here. And then 0 could actually be all sorts of things. It could be that it has, blah, the points are just thrown up there. Or it could be very particular patterns, but they're not linear, right? So this is 0, but there's a pattern to that, right? This is 0, but there's a pattern, very distinct pattern. Okay. So now we're going to look at these graphs down here, and we're going to apply, oops, hold on, I got to go back to ours. There it is. So we're going to look at these graphs, and we're going to apply these different correlation coefficients to these numbers, or to these graphs. Okay, so let's see here. Well, this one, oops, hold on. Okay. C, I think, is the most obvious. C has an R value of equal to 0.1 or equal to 1. And then H would be -1. All right, now what about A and B? Well, A is positive and it's quite strong, so that's probably the 0.85. B is negative, and that's also even stronger, so that's got to be the -0.94, right? The closer you are to 1 or -1, the stronger you are. So these two are 0.85 and -0.94. This one I said over here was 1. This one's kind of hard to judge. It's negative, but it's pretty weak. So I'm betting it's the negative point. Well, there you go. I've got them in here now. So this one's -0.54 probably, and this one's -0.33 because that's even weaker. That's a little bit hard to tell from these two graphs, but what makes this one even weaker, or excuse me, this one down below even weaker, is the points are even further away, kind of more scattered from the line. But those are both pretty terrible, to be honest. Down here, it's got to be the positive weak one. So positive, let's think, 0.42 or 0.17. Where's the other graph? Oh, okay. So this one's 0.42, this one's 0.17. Because if you take the line out of it, look at how that just looks like kind of a big blob. So that's the 0.17. All right? They're both pretty terrible, though. I mean, let's be honest. 0.42 is not exactly a glowing recommendation, right? That counts as weak as well. So these are all weak. Both of these and this one. All right. Now, how do you compute the correlation coefficient? I have a video for that. Let me pull that up. You have to do one thing first. You have to turn diagnostic on your calculator. And then I have the instructions right here. I can't show you right now because the computer won't run my calculator program right now. But here we go on my channel, right down here under Math 133 Calculator Tutorials. Right there, Chapter 4, Sections 4.1, 4.2, 4.3. I go through how to do that with a calculator. All right, so there you go. And I found, with the calculator in that video, I found this correlation coefficient to be -0.688. All right, now the predictor variable here, sorry, let's back up. So that's all the instructions, and this is the example that I use it for. But let's back up and actually look at this example. So this is the percent of students who receive free or reduced price lunches compared with the percent who pass the math portion of the state exam at public schools in Sandusky, Ohio. All right, so the predictor variable will be the percent of students on free reduced lunch. And the response variable would be the percent of students who pass the state math test. All right, now the correlation coefficient, again, the instructions are right here. You'll have to turn diagnostic on, and you can do that, and then follow that video. It's very simple, and it shows you how to do it. All right, so now what kind of relationship is this? This is your R value of -0.688. What kind of relationship does that say to us? Well, It says that it's a moderate negative linear relationship, which means this means that as free reduced lunch percentage increases for a school, then the percent of students that will pass the math test, pass the state math exam, goes down. Which makes a lot of sense. I mean, what is free reduced lunch really measuring here? It's measuring poverty, right? So when you have students that are poor, can't afford lunch, right? Then they're perhaps less worried about passing their math test and more worried about, working a second job to try to pay the bills at home, trying to make sure that they have, food and water, et cetera, et cetera. All right, now why is this an observational experiment? Observational study, not an experiment. Well, you didn't, the researchers did not control poverty, wealth, i.e. the percent of students on free reduced lunch in a school. Right? They didn't look at, you child, you get free reduced lunch. Next child, randomly, you don't get free reduced lunch. They didn't do that, right? So they're not dictating who gets free reduced lunch. So they're not controlling the poverty wealth of a school district. Of a school, I should say. They are merely observing what already exists, right? So they're not saying, I will give you food, and I won't give you food. That would be an experiment, right? That's not what they're doing. They're just observing who already gets free and reduced lunch food and who doesn't. Okay, so why is that an issue for us? Well, it makes it so that you can't argue that free reduced lunch causes low exam scores. You can't say, if I just want my exam scores to be higher, I'll just get rid of all free lunch in my school. That's not how it works, right? The free reduced lunch is a symptom of a larger problem, right? And that's your lurking variable. So you can't say that free reduced lunch causes low exam scores, right? The free reduced lunch percentage is an indicator for larger issues that are affecting students' passing rates, math test rates, right? i.e. lurking variables, right? In other words, lurking variables such as, let's think, probably the education level of parents, right? That would affect income, obviously, is what you're really measuring here. So the income of the parents, income of the family, whether the parents, number of jobs the parents have. Because if a parent has 2 jobs the parents have, right? Could be, well, I guess I should say parents have, right? So, if you're working 2 jobs and you can't afford the time to read to your kids, that kind of thing. The affordability of housing. Oh, and healthcare. Let's not forget healthcare. That's always a big thing. If your kids are sick, if you're poor and sick, then you're not going to be able to study math, say. Always remember that you don't want to just say, because of lurking variables. What? Give us some examples. Show us that you understand the context of this. So the lurking variables in this case would be, all these things. There's more, right? There's all sorts of things that affect passing rates in an American educational system. All right, so then, let's see here. So determine whether or not a relationship is linear. All right, so there's lots of different ways to do this. And no one way is the right way. It's more that they're kind of a combination of these factors that determine whether or not a linear relation exists. So one is you kind of look at the scatter plot and see, does it look linear? 2, you kind of check out the value of the critical value of R, which we're going to do on this page. I'll explain what that means. The residual plot thing, which we'll learn in section 4.3, and you do some more rigorous stuff which would be chapter 14, but we're not covering that in this course. That would be like a Stats 2 course. Okay, so all these things in concert kind of help you determine, is it linear or not, right? It's not enough just to have a strong R. You kind of want all these things in combination. You want it to look like linear. You want it to, act like linear. And these are some of the things you can do to try to check whether it's linear or not. All right, so how are we going to do step 2? This checking the critical value piece. All right, step 1, you determine the value of the correlation coefficient, which we've done. That was back here. R was negative 0.688. Let's see, to determine the absolute value. Oops, we want to do the absolute value. Okay, so let me do that. Step 1, and let me type that in. Hold on one sec. All right, so step 1, take the absolute value. Well, absolute value always makes it positive. So basically all I'm saying is take the positive of your correlation coefficient. Step 2, find the critical value in table 2. Now, this is in your course pack somewhere, but I also have it right here. So if you look in the back at the neon orange pages, somewhere in there it should have the correlation coefficient table. You need to figure out your critical value. It's based off of your sample size. So let me go back to the table here, and we can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So n was 13 for us. And you just count and figure out what it is, right? N equals 13. So that means the crit value is equal to, and you got to look at the table for it, 13 goes with 0.553. So 0.553. And then step 3, if your number is passed, if the absolute value of the correlation coefficient is greater than the critical value, then we say the linear relation probably exists. So that's what I'm going to put right down here. Step 3. R equals 0.688 is greater than the crit value of 0.553. So a linear relation probably exists between free reduced lunch percentage and the percent of students passing the state math exam. Done. All right, so let's get this last page done. So I have a little cartoon right here that Jason Love sold to me, which is statistics show that crime rates rise with the sales of ice cream. Now do your part and move along. Which of course is making fun of the age-old problem that correlation is not causation. It is true, totally true, that ice cream sales and crime go together. But that's because there's a lurking variable, i.e. the seasons / the weather, right? You are way more likely to steal a big screen TV in the summer than you are in the winter because, well, winter you could fall, hurt yourself, and snow leaves tracks, right? Okay, so now what about the free reduced lunch? Well, we already said education of the parents, money, etc. We had a whole list of them. Lurking variables are the reason that correlation is not causation. And again, you're going to want to give specifics. Don't just say lurking variables. What kind of lurking variables? Think about this problem a little bit. All right, so here's another one. A positive correlation exists between shoe size and number of years studying math, right? And this is what it'll look like. So this makes sense, right? Yes, it makes total sense, right? Yes, it makes sense that shoe size increases as years studying math increase. That explains my big feet. Increase, years studying math increase, right? But why is that happening? There's a strong correlation. So strong correlation, strong. Right? And it's positive, right? As the little graph I drew shows. But why is it happening? That's because of the lurking variable age. Naturally, kids with bigger feet have been studying math longer because they're older, right? All right, we're done with section 4.1. And hopefully now you understand this little nugget right here, which is correlation is not causation. Maybe this class is helping. Well, maybe, because you can't prove it, right?